We'll be doing today is calculating a position line and bearing using the sextant altitude of the celestial body based on the intercept method. So the intercept method, also known as Marx-St-Hilier's method, can be used to derive the position line and the bearing from the celestial body. Now what happens is the sextant altitude of the celestial body can be used to plot the ship's position at sea. The concept is based on bearings, because with with terrestrial objects on land, what we can do is use the concept of bearing and distance. So obtaining a bearing of the body and then the distance of the body can give us the position of the ship. But with celestial bodies, of course, it is so far away, it's light years away from us, we cannot use the concept of bearing and distance. So we pretty much have to work with bearings, or the angles at which the ship has a bearing from the celestial body. So if we can obtain a sextant altitude, and if we have the other details such as the time of the altitude and some of the other details, we can actually obtain an intercept and a position line which gives us the bearing and an approximation of where the ship is at sea. The intersection of two such position lines gives us the position of the ship, two or more position lines. So the more the number of position lines, the better it is, because it gives us higher accuracy. Now in this video I will only focus on deriving the position line and the intercept of the bearing of the celestial body, and in my next video, part 2 of the series, I will show you how two position lines can be used to plot the ship's position at sea. Alright, so we'll do the plotting in my next video, otherwise this video will become a bit too long and you will lose track of what we are talking about. It becomes too lengthy and then you lose track, you will lose interest. Alright, so let's talk about the intercept method, and the example here will be using sun. If you see my previous videos, you know how to derive the LHA and how to get the true altitude of the star, the planet as well. So the principle remains the same, so don't worry about it. So we'll use the example of the sun. It's a pretty long question to solve, so it takes a bit of time, so just try to hold on the interest here, and if you kind of drift off, then pause the video, watch it again later on, or you watch it in sections, depends on how you want to do it. Alright, so it's a bit lengthy, but let's see how you go with it. Alright, so we've got the sun's lower limb as a celestial body, and we've got a DR position as well, right? So the whole idea behind this is that we've got a DR position, a dead reckoning position rather, and I've been saying DR position in a number of videos. Probably I've never mentioned that DR stands for dead reckoning. Dead reckoning is an approximate position. So we've got an approximate position, and those were the days when we didn't have GPS on the ship, so or the GPS would sometimes stop giving signals. Not on the modern ships. The modern ships, you are getting signals, you have multiple GPSs actually, but those days you didn't have multiple GPSs, or the GPS would not give signals sometimes. So you would have a DR position, an approximate position, then you would use the sextant to get an altitude of the celestial body, and from there you could plot the ship's position. Alright, it used to be called the fixed position. I'll show that how to do that in my next video. So the sun, sextant altitude of the sun was 16 degrees and 46 minutes. The index error was nil, so 0. Height of eye is 9 meters, and the chronometer had no error, showed 00290. Alright, so this is the chronometer time. To derive the GMT from the chronometer time, we need a hint in the question. The hint is given here, that it is 15:29 ship's time on the 25th of October. Alright, so this is the hint given to us. So let's derive the GMT time from the chronometer time. So if the chronometer is shown as 0029000, so the chronometer pretty much looks like an analog watch. Now of course on the ship we can get an idea of what the time is, whether it's 00 or 12 hours, but for academic purposes here, or for numerical purposes, we are not really sure that the chronometer time 00 could mean 00 in the early in the morning or 1200 hours in the afternoon. So we need to derive the GMT from there. So because the error is nil of the chronometer, the GMT time is same as the chronometer time at 0029. Now we need another hint here. So what happens is, now we have to apply the zone. Remember the zone, and the zone is west here. We are in the west longitude. So if you watch my other videos, you will see that I've explained the relationship between longitude, zone, and zone time. Now how do we get the zone? So I'll just quickly recap, give a recap of how we get the zone. So the zone we get from is longitude in time, LIT. LIT we get from dividing the longitude by 15. So if in this case you divide 142 degrees 15 minutes by 15, what you will get is as 142 degrees and 15 minutes divided by 15 is 9 hours 29 minutes. So 9 hours and 29 minutes. Now since this is less than 30 minutes, the zone would be 9, and because we are in the west zone, that means GMT should be ahead of us, so the time on the ship will be behind GMT. That's why we subtract it. Now in both the cases, when we subtract 9 hours, in one case we get the zone time as 15:29, and in the other we get the zone time as 0329. Now this is where the hint comes in handy. Now the question says, or the hint given in the question is that it's 15:29 ship's time on 25th of October. So immediately I know that the second case is not the correct case, so I will cut it off, because the zone time here is 15:29 as well, and it's 25th of October. But because we are behind GMT and GMT is 9 hours ahead of us, that means at GMT the date has already changed to 26th of October, and that is why your GMT is on the 26th of October 0029, right? Because our ship is in the west longitude, GMT is on the Greenwich meridian, they are ahead of you in terms of time. They are 9 hours ahead of you. So basically it's 25th October afternoon 1500 on your ship, but it's already past midnight on the 26th of October at the Greenwich meridian. Alright, so I have explained this before. Watch this part again if you found this a bit confusing, but remember to use the hint given in the question to get an indication of what the GMT would be. And remember, the rest of the question has to be done using the GMT time and not the zone time. Many people make the mistake and they use the zone time for further calculations. Don't do that. Use the GMT time. Alright, that's why I've written it in a box and highlighted it to make sure that you don't use the incorrect time. Alright, having said that, now we have to go to the almanac. I have shown in my other videos how to obtain the LHA and declination of the sun, so I won't waste too much time on it. So what I'll do is I'll quickly show you that the GHA for the 26th of October for the sun at 00 hours. So you can see this is 26th of October, right here. The sun is right here, 00 hours is right 20, we need the 26th of October, right? So 26th of October at the bottom here. So here, this is where GHA is, this is where your declination is, this is your D value, right? So these are the values that you will be using to get your GHA and declination and D value, or else watch my other videos where I've explained in detail what to do with these values. So I'll quickly go back now and I'll continue with my calculation. So these are the values I have used. The increment value is obtained from the increments page in the nautical almanac, and I'll quickly show you what it looks like. So we need the increment for 29 minutes and 00 seconds, right? This is for 00 hours, and so the increment for 29 minutes 00 seconds, let me go back here, and if I go back here, so you can see that for 29 minutes, so 26, 27, 00, 26 is here, is that right? I've forgotten what the time was. It was 0029, I'm sorry, not 26 but 29, right? So for 29 increments for sun is here. Okay, bear with me, this is a painful process that I take you guys through, right? So this is the 29 minutes column, this is the sun, this is the 00 seconds, this is where the increment is. You get the D value for 0.9, here 0.4. the declination was increasing, so we'll add it. So I've explained all that to you in my previous video, otherwise just watch my previous video where I've shown you correction of altitudes, and then you can get an idea. So I don't want to waste too much time here on getting these, but I just quickly showed it to you on how to get the increment and the decorrection value for the declination. So I go back here, and you can see that I've put in the increment here. This GHA is for 00 hours 29 minutes and 00 seconds after applying the correction. You can see the declination is applied as well, so I've got the declination here. The longitude in this case is west, longitude west, GHA would be best. I would subtract my longitude to obtain my LHA, right? LHA value is less than 180, so I have named my LHA 0 to 180. So the rule of thumb is 0 to 180, you name the longitude west, and if it is greater than 180 to 360, you name the, not the longitude, sorry, the LHA, you name it east. All right, in this case it's less than 180, so the LHS will be named west. Right, so if your longitude is west, GHA is less, so we subtracted longitude from the GHA to get the LHA value. We've got the declination and we've got the latitude as well over here, so I've recapped it over here. Right, what I want to focus here on more is this formula here. This is the formula that we use to calculate something called CZD. Now CZD stands for calculated zenith distance. Calculated zenith distance. This is my terrible handwriting, I should write it again probably. Right, so let me write it again. Calculated zenith and distance is what CZD stands for. There is a formula here, cos lat times cos dec times cos of LHA. Depending on the names of the latitude and declination, you then add or subtract it to a product of sine of lat and sine of declination. So you can see here I have worked it out here. You can follow me here. So cos lat value, cos declination, cos LHA value, and a product of these three gives me a value called x. Now I have stuck to 5 decimal places because it pretty much gives you a good accuracy. Don't use 2 decimal places, try to use 3 to 5 decimal places, that gives you better accuracy. Alright, and then I've got my sine lat and sine declination value as well. A product of these two gives me my y value. Now whether I need to add the x and y or subtract it depends on the rule that if latitude and declination are same names, I will add them. Right, the rules are given here. If they are different names, I will subtract them. Now in this case here, because the latitude and declination are different names, one is north and the other one is south, I will subtract them. That's right, so that's what I've done. I have subtracted x from y. So what I will do is I will delete the plus sign then, so it makes it easy for you. Right, so what I will do is I will subtract it, and a cos inverse of this value, a cos inverse of 0.291114 will then give me a CZD, or a calculated zenith distance, of 73 degrees 4.4 minutes. Alright, so see the formula above that shows the formula for cos CZD, and you know how to do that. Right, so just try to match your values with mine. Make sure that if they are not matching, you recheck your values, because mine are correct, I can tell you that. Alright, so once we've got a CZD, or calculated zenith distance, we need to calculate our true zenith distance, and we calculate our true zenith distance from the sextant altitude. I've shown in my separate videos how to do that as well. It's pretty straightforward. You've got your sextant altitude, index error was nil. From there you get your observed altitude, then you apply your height of eye correction from the height of eye tables. Your height of eye is, in this case, is 9 meters. So if I go back into my nautical almanac and I go back on the first page of the nautical almanac, you can see here is that my height of eye is given, give me a minute. That's right, I've got it here. So my height of eye is given here. It's a dip, is the height of eye, and let me erase the rest so that you guys don't get confused with what we are doing here. So height of eye, or the dip table, is given here for 9 meters. If you go down 9 meters, and if I kind of zoom in, you can see for 9 meters the correction would be somewhere here, which is minus 5.3. Alright, so I'm not going to waste too much time here. I'll quickly go back to the calculations. So you can see that that's the height of eye I've used, is minus 5.3. A subtraction gives you the apparent altitude. Taking the apparent altitude, we go back to where we were. We found our height of eye for total correction. So apparent altitude is 40.16 degrees 40.7, and it was a sun's lower limb, and it was the month of October. Alright, so I've explained all these things before in my previous videos. At the risk of repetition, I keep repeating myself. Watch my other videos where I've shown you how to correct the sextant altitudes to obtain the true altitude. Alright, so I'll show you what to do with this. Go back to the page from where you get your height of eye from. This site here gives you the total correction for the sun. The month is October, so it should be somewhere here. The altitude, or the apparent altitude, is 16 degrees 40.7. It's the lower limb, right? So we have to go down the lower limb column, which is this column here. And if I zoom in here, 16 degrees 40.7 would be somewhere here. The correction should be plus 13.1. So that's how I got my correction from. So, and that's what it says here, 13.1, right? I will add the correction because it's lower limb. Once I get my true altitude, I subtract it from 90 degrees to get my true zenith distance, because true zenith distance, or TZD, is equal to 90 degrees minus true altitude. Alright, Once I do that, I get my true zenith distance, which is TZD, true zenith distance. That's what it stands for. Alright, in case my pronunciation wasn't very clear. Now what I have to do is to calculate my intercept, I have to compare the true zenith distance to the calculated zenith distance. Alright, and there is a rule of thumb again. Now there are a lot of rule of thumbs I teach you guys. So yes, there is another rule of thumb. I'll erase this and I'll write it next to the values here. So the rule of thumb is that if you compare the true zenith distance with the calculated zenith distance, and if true is less or true is tiny, then the intercept is named towards. So normally we call this rule TTT, true tiny towards. So if true is less or true is less than what? Less than CZD, right? And of course, if true zenith distance is more than CZD, then you name it away. So you have to remember the top one, the triple T, true tiny towards. That means if true is less than CZD, it's called towards. But in this case, you can see the true zenith distance is more than the calculated zenith distance, and that's why the intercept is a of course always the difference between the two, and the difference between the two is 1.8 minutes, and the naming is away. So it's 1.8 minutes away. Right, with that you got your intercept. So one problem solved. Alright, later on I'll show you how to plot this. I mean, towards the end of the video I'll show you how to plot this, but how to use this to plot the ship's position will be shown in the next video, where I'll show you how intercept is used to plot the ship's position on the chart. Alright, so note down this intercept, don't forget this intercept, and then what we do is what we have done before in calculating our compass errors. We calculate the components of the bearing A, B and C. A is calculated as tan lat divided by tan of LHA. Straightforward, stick to 2 decimal places this time. You can go to more of course, but I stick to 2 decimal places when it comes to A, B and C's. You name it opposite to latitude, unless it's always named opposite to latitude unless LHA is between 90 and 270. In this case, is LHA between 90 and 270? Let's check what's the LHA. No, the LHA is 49 degrees, so it's not between 90 and 270, so it will be named opposite to the latitude, and latitude was north, so we'll name it south, right? Then we calculate the B component. The B component is calculated as tan declination divided by sine LHA. I've written the formulas here so that if you don't understand what I'm saying, at least you can follow what I've written. And you name it same as declination. Now in this case, of course, the declination was south, as you remember from before, and that's why I named it south. Right, now how do you get your C component? Your C component is depends on A and B, so if they are the same name, such as south and south or north and north, then you will add them, otherwise you subtract them. In this case, of course, they are the same names, so you add the two and you get your C component, and you retain the name of course the larger, but in this case both of them are south, so it will be south. Alright, why all this is important? You'll slowly see. Once you get your C, you calculate your azimuth. How do you do that? You use this formula here, tan azimuth equals 1 by C times cos lat. Find out the value of C by cos lat first before you divide 1 by it. Alright, just the way I have done it. Once you get this, so your tan azimuth here equals 1.21630. So a tan inverse of this now will give you the azimuth value, right? In this case, again, this is what I've shown here, so I don't need to repeat myself, so I'll just delete this here, right? So a tan inverse of the value gives you your bearings. Now your bearing in this case is 50.6 is what you get in your calculators. Now you better round it off because it's a bearing, so it will be difficult for you to not only difficult, but it's kind of an approximation or impractical to plot the bearing on a chart in decimals. You can't do that, right? So just round it off to the next number if it's more than 0.5. So in this case I have rounded it off to 51 degrees. Now where do I get my south and west from? Well, I get my south from the name of C. Remember, C, I named it same as C. And west, where do I get it from? From my LHA. So if LHA was between 0 to 180, I named it west. In this case it was west because it was 49 degrees, and if it would have been more than 180 to 360, I would have named it east. So if it's south 51 west is my azimuth, my true bearing becomes 231 degrees true. How is that, you ask me? Well, this is how it's done. I have shown this in my other videos, but I'll just repeat this again. This is south and this is west, right? This is north and this is east. This is 270 and this is 180. So if I'm south 51 west, that means I'm going something like this. I will add 51 to 180 to get my bearing. So 180 plus 51 gives me 231 degrees true. And that's what I have as my bearing here. Once I get my bearing as 231, I need to get my position line. A position line is a line perpendicular to your bearing line. So a line perpendicular to 231 degrees true in this case. So how do you get your position line? Just add 90 to it. When you add 90 to it, what do you get? In this case, you get 321. And if you subtract 90 from it, what do you get? You get 141. That's what you do. Just subtract and add 90 from the bearing and you will get your position line. Now what does this mean is, this is what it means. So basically you are in a DR position. Let me show you what this means. This is your DR position, right? Let's see. Now ideally this is what it means, is that you obtained a bearing of 231 degrees true, right? And an intercept of, remember the intercept we calculated? You shouldn't forget the intercept we calculated. Here it is. The intercept is 1.8 minutes away. So when we say away, that means we are away from the bearing. So if the bearing is 231, we should go away from it. That means if the bearing is 231, we go away from it completely diametrically opposite to 231 degrees is 18 minus 180 is 051 degrees. So instead of going towards 231, I will not go towards 231. I will go away from it by 180 degrees. I will go 051. I am going in the direction of 051 degrees true, and I measure 1.8 centimeters, or 1.8 miles rather, is the intercept. So this is, say, example 1. This is 1.8 away. This is the intercept, right? 1.8. Now when I cut 1.8 here and I draw a perpendicular line here denoted by single arrows, which shows my position line. Now this position line is 141 to 321. Alright, now the good thing about this is you can watch it again. If it was a class, I would be repeating myself a few times, but just watch what I did again. So what I did was that I used the three information that I had. I had the intercept, right, as 1.8 away. I had the bearing of 231 degrees true, and then of course I had the position line that said it was 141 to 321, right? This is what I used. Now what I did again, and I'll show you here, right? This was my DR position, approximately DR position. So and because my intercept is 1.8 minutes away, that's 1.8 miles away, instead of going towards 231, which would have been here if it was a compass rose, I go towards 051, opposite to 231. This is 180 degrees away from it. I measure 1.8 miles on this line here, and I mark it, and then I draw a perpendicular line. This is my position line. Now what does this mean is, this means that because I knew only the dead reckoning position and approximate position at sea, when I took my sextant altitude of the sun and I've got my position line, what it does is basically gives me the bearing from the sun. Now the bearing from the sun could be, it could be a very long line, but because of these calculations, what we know is that our ship lies somewhere on this position line of 141 to 321. It lies somewhere here. And through our calculations, I know statistically I am somewhere very close to the intercept terminal point. This is called the ITP, where my intercept is cutting the position line, intercept terminal point. Alright, so what I need is, this is my position line. What I need is another position line from here. So the intersection of two position lines can then give me my ship's position at sea. It's called a fix. Now in my next video, this is what I'll show you. I'll show you how to plot the ship's position at sea on the chart using two position lines. So normally what used to happen at sea is that you take a position in the morning, say at about 10 o'clock, right? You get a position line intercept like that, and then you probably transit a few miles along a course. In this case, let's say it was on a course of 220 degrees true, and you transit for till the noon position. You come at a known position, you don't know where you are, you have got you transfer this one here, right? You transfer this one here. When you transfer it, you denote it by double arrows, and then you get another position line. It could be a meridian passage, which gives you a latitude by meridian passage, or it could be another intercept and bearing. The intersection of these two gives you your fix. So see, I won't worry too much about this at this stage. This is just extra information I'm giving you. Alright, I was trying not to make this video very lengthy, but it is becoming lengthy here. I'm just giving a brief background here, but I'll show you more about this, and I'll show you how to practically plot it, how to practically use this information to plot the ship's position at sea. Alright, so don't worry too much about the later section. Just go through it if you want to go through it, but focus more on the calculations above. See what I have done, go through it in stages. I have not wasted too much time on things that I've explained before in my previous videos, so make sure you watch it again and again to get a good understanding. Alright, I'm happy to receive any questions through comments. Thanks guys.